Where's my pen? Okay, here. We're going to learn this new thing, the CLT. Okay, it's not a cucumber, lettuce, tomato. It's a central limit theorem. Anyone who have learned anything about statistics for a little bit, maybe less than a semester, maybe one semester, if you ask him, have you learned CLT or do you know CLT? He should tell you, yes, that's a central limit theorem. If he doesn't know, that means he's not a good statistics student. Okay. All right. Now, what does that mean? That means, basically, it's very simple. That means if population distribution of x, I just make it here, okay, is normal. Population distribution is normal, or if I don't know the population distribution is normal or not, or sample size n is greater than 30. So either this or that, then sampling distribution of x bar is normal with mu of x bar is the same as mu. Standard deviation of x bar is the standard deviation over square root of n. Okay, if you remember, I talked earlier that I asked each of you to get 50 students, ask 50 students for their age and then get the average of that, you give me an x bar, right? So if I have a 100, if I have 200 students, I ask everyone do the same experiment. Everyone will bring back to me an x bar. So I will have a lot of x bars. And if keep doing this again, each time the sample size is 50, so I get a lot of x bars. I'm going to get tons of x bars. And what is the distribution of those x bar? It's normally distributed, and the mean of all the x bar should be the same as the population mean. This is the population average age. So the standard deviation of our x bar, you look at the distribution of this distribution of the x and the distribution of x bar. So this is the distribution of x, and here's the distribution of x bar, because each x bar is already getting closer to the mean, right? So it's going to have like a narrow and a taller distribution like that. Okay, it's going to be like this shape. So that standard deviation is much smaller. How smaller is the original? This is standard deviation, whatever it was, divided by the square root of n. So if you think about it, n is a 50, square root of 50 is a slightly more than 7, right? 7 point something. So that's going to be the age. When we talk about the age distribution, it has a variance or standard deviation. It's going to be that standard deviation divided by 7. So it's only 1/7 of the x is the standard deviation. Okay, it makes sense? Yeah. All right, now let me give you a couple of examples to do that, to understand this. Okay, so the first example, let me see the first example here. All right, the airline. Right, so they have all the people sitting there, and then this engineer said right now the current seat width is 16.6, and he said maybe I can reduce that to 16.0 inches. That's what he thought, and he want to think, is this right? Is that a good idea? If you shrink, if you make all the seats narrower, then you can put one extra passenger somewhere. I don't know. It was his idea. Okay, so what we know is this: we know for the male, adult males, all the adult males have hip width that is normally distributed. Hey, good, I love that. It's normally distributed, means population. It's more normal, right? And that mean is 14.3 inches, and the standard deviation is 0.9 inches. Okay. And how many seats in this airplane? 126 of them. Now, first question. What is the probability that a randomly selected adult male has a hip width greater than the seat width of 16? What is the probability that a randomly selected person, random selected adult male, his hip width is greater than 16? So that's X. It's a good habit, isn't it? Right? All right. Now we talk about an X. For X, what is the mean? 14.3. And what is the standard deviation? 0.9. All right. Now what is the where is the 16? X greater than 16. Somewhere here, isn't it? 16. Okay. And X greater than 16? To the right of it. Greater than 16. So we'll talk about this probability. So do you notice there's something missing, which is here? We need to find the z-score for that. So the probability, okay, here, z-score will be 16 minus mean divided by standard deviation. Where's my calculator? Here. So I have 16 minus 14.3. I got a 1.7, then divided by 0.9. So I have a 1.89. So here's 1.89. Therefore, the probability that X greater than 16 is the same as the probability that Z greater than 1.89. Again, you can use the table you have, either use a negative z-score, find the negative 1.89, and then you find this little blue area, which is the same as that one because this is symmetric, or you can use the positive z-score because right now it is positive 1.89. So you find 1.89 and then look at the table to find the probability, and then which is this blue area, and then subtract that from 1. Either way. Okay, so I would like to just go ahead and jump into negative 1.89. So negative 1.89 is 0.0294. 0.0294. So 2.94% of the chance that a randomly selected male, his hip width is greater than 16. What about 16.5? 16.6 originally, right? So I can quickly do that. I can quickly just do it again. So here's a 0, and here's a 14.3, and here's a 16.6. I do this very, very quick. And here's a z, here's x, and a sigma is 0.9. So the z-score is 16.6 minus 14.3 over 0.9, which is 16.6 minus 14.3. I got 2.3 divided by 0.9. So I get 2.56. 2.56, which is here, 2.56. And then I look at negative 2.56. It's so small. 0.052. So the probability that x greater than, sorry, I forgot to shade that, greater than 16.6 is the probability that z greater than 2.56, and which, oops, I forgot again, 2.56. I'd better write it down somewhere. Okay, 0.052. 0.0052. See, it's only 0.5%. Okay, so or 0.52%. C. So if all the passengers, all 126 passengers on board, they are adult males, and originally we have less than 1%. It's only 0.5% of the adult male they're going to complain, or they need more accommodation, or they need somebody to take care of them. But if you want to reduce that to 16, then you're going to have close to 3% of the people complain. All right. Now, this is like the review. All right, now next question. What is the probability that the average of 126 people's hip width is greater than 16? X bar. So then this is the sampling distribution of X bar, and we know by CLT. Okay, by CLT, we don't really care about the population distribution is normal or not, since in this case we have n equals 126. That's fairly big. So mu of X bar, we need to find the sampling distribution, which is the same as mu, 14.3. Standard deviation of X bar, which is the standard deviation over square root of n, which is 0.9 divided by the square root of 126 equals, okay, so hold on, let me see, 126 square root, it doesn't have that, which is 0.9 divided by 1.225, so that equals, okay, so 0.9 divided by 11.225, so the answer is 0.08. I think in the book they just rounded it to 0.1, but I let me keep that. Okay, so we're ready to draw the graph. We always draw Z, okay, 0 and Z. And now, okay, now we're going to see the difference. We talk about the distribution of X bar, so we have to have X bar here. And in this, we should put the mean of X bar, which is 14.3. And here I should put a standard deviation of X bar, which is 0.08. Okay, you see the difference? Okay, now it's X bar, not X. All right, now we look for what is the probability that X bar is greater than 16. So here's a 16, and we're looking for this area. So we need to find the z-score for 16 minus 14.3 divided by 0.08. Now you see the benefit of why I ask you to write the standard deviation here, because you won't get confused about which one you should. You should use 0.9 or you should use this. No, you see here, this number minus mean divided by the standard deviation right away. Okay, so you know you can either use let me just write here. You can either by z equals X bar minus mu of X bar over standard deviation of X bar, or z equals X bar minus mean divided by standard deviation over n. Either way, but that's the same thing, because this one is that and this one are the same. So then let me quickly do this. So 16 minus 14.3 divided by 0.08, you get a 21.25. So here is a 21.25. What do you think? On your z table, the maximum z value, or the maximum z score that you have on the table, is only 3.99. So anything greater than that, which means this area is almost 0. So the probability that the average hip width of this all 126 adult males is greater than 16, which is the same as z greater than 21.25, which is almost 0. So now the engineer said, wait, I can reduce that to 16, because even I reduce that to 16, there's almost no chance that the average of all the 126 adult males, the average of that is greater than 16. It's going to be less than that. Well, it's true. But when you talk about this, you shouldn't do that. You shouldn't use the X bar. You shouldn't care about the average hip width. You should care about each individual. Okay, so of course there's almost no chance that the average of them, but when you get the complaint, you get the complaint. So even like we just did earlier, before when the seat width is 16.6, there's only 0.52% of the people, adult male, are going to complain. You reduce to 16, from 16.6 to 16, you only reduced by like this little. Look how many people that you have to take care of. Okay, so it's quickly more than about 2.5% of the people who is going to come to you. So that's not what you want. Okay. All right, now let's look at another example. It's about the body temperature. Okay, the body temperature. We always believe that the human body temperature is 98.6 degree Fahrenheit as the average, and the standard deviation is 0.62 degree Fahrenheit. Okay, the mean and the standard deviation, they should have the same unit. Okay, so that's what a commonly believed. Now, a group of researchers, they just got a sample, and their sample size is 106. So they did a sample of 106, and they get this 106 people, and they measure their temperature. Guess what they find? They find the X bar is 98.2. Okay. So this is about the population. This is about the mean. If you are the director of this research, what would you think? You think this 98.2, you look at this 98.2, you think, it might be too low, right? If it's just one individual, if I have the population, body temperature, human body temperature, the body temperature is normally distributed with this mean, with this standard deviation. Okay, let's do a little side work. What is the probability that you get one random person's body temperature 98.2? It's going to be like this. Okay, here's a 0, here's a Z, always. Here's 98.6, and here's the X, and the standard deviation is 0.62. Where is 98.2? Which is here, right? So here's 98.2. What's the chance you get that low? 98.2 or lower. So your Z score will be 98.2 minus 98.6 divided by 0.62. So the answer is negative 0.4 divided by 0.62 is negative 0.65. All right, now we look at the negative 0.65, negative 0.65 is here. It's 2578. Sorry, 2578. So here, 0.2578. Negative 0.65. So the probability that you get a simple random sample, randomly selected a person's temperature as low as 98.2, which is the same as Z less than negative 0.65, which is 0.2578. It's about a 25%, 26% of the chance. So there's a pretty good chance, right, that you have one person's temperature as low as or 98.2 or less. But what about this 106? Remember, n is 106. What is the probability that this average is less than 98.2? We ask for this. All right, now we know mu of x bar is the same as mu, as we believe. Standard deviation of x bar is the standard deviation over root n, which is 0.62 divided by the square root of 106, which is 106. Square root is 0.62 divided by 10.29563. I just write a little bit more decimals so it can be a little bit accurate. Divided by 10.29563, I have 0.0602. Wow. All right, now I'm ready to draw the graph. 0z here, x bar, and the mu of x bar is 98.6, and the standard deviation of x bar is 0.0602. Where is 98.2? Here. And what is the chance that this x bar is less than that? So z score will be 98.2 minus 98.6 divided by the standard deviation. Okay, so it's going to be 0.4 negative divided by 0.602. So it's going to be 6.64. Again, sorry, negative. So this is much further than 3.99, right? So it's negative 6.64. So the chance is almost 0. Therefore, the probability that we have this x bar less than 98.2 is the same as z less than negative 6.64 is almost 0. Okay, in your quiz or homework or exam, I want to see every single step just like this. So I know how do you get the answer. Don't just simply just put a number, drop the number somewhere and then give me the answer. I cannot take that. So I really need to see all the steps, okay? All right, now, what does that mean? That means there's almost no chance, very less chance, you have the average body temperature of 106 people's body temperature 98.2 or lower. Okay, so if you are the director of this research, when you see this number, you say, it's a little too low. Then you do this work, you found that the chance is almost 0, so there are two possibilities. I think there are two possibilities. Number one, you have a very strange sample. So this sample is really rare, or there's something wrong with your sampling method. Maybe you measure them outside of the winter time. I don't know, or it's just something about your sample wrong, or your commonly believe the human body temperature average 98.6 was not right. So either a sample's not good, or the assumption of the population mean or standard deviation or something like that was not good. So either way, because there's really almost like a no chance, almost very tiny slight chance the average is 98.2. But if you just talk about it, just one person, randomly select one person, his body temperature get that low, the chance is almost like a 26%. So that's not a problem. But for the average, it is a problem. Okay, so now you see how do you use the central limit theorem. You use the central limit theorem when either you have the population, a normal distribution, or the sample size is really big, greater than 30, and then CLT tells you that your sampling distribution of x bar is going to be normal with a mean, with this standard deviation. All right, and then you can just go ahead and figure out a lot of things and using pretty much what we learned earlier. Okay.